Good morning. Hi. Just getting some stuff done on Mini. Around chicken bits and spinning up CPUs. Things that need to go in there. Where is that thing? I want to see how Linux does the definers, because I might use something similar. What's on top of that? Where is that documented? I saw the registers, the OS lock thing. I saw the registers, but I don't know where they actually explain what all that is about. Yeah, but like it's not even using this constant. Yeah, I don't know. No, I didn't do SMP with Python yet. I want to put the chicken bits in C first, so I can call them. Also, I need to do the chicken bits for Firestorm. I'm gonna figure out what the sanest way of doing this is, but because it's going to the assembler, I guess for now it's just gonna be what distro am I using? Gen 2. No, that doesn't make any sense, does it? is this up actually? Asahi is Arch Linux, so it's going to use Pacman because it's Arch Linux. The same thing? No. Wrong one here. 361510. Oh yeah, I forgot to clang formulate this. I guess it's fine if dependencies don't get formatted, but that header file is going to be. Yeah. Actually, I don't really want to do that. The HID bits were not reverse engineered by me. These actually come from Pongo OS, but they would have come from like Darwin because there's no way of doing this other than looking at the original code because it's magic CPU chicken bits. You literally have to do this exact sequence of code to make the CPU not explode. So, if you disassemble Mac OS, you will find the sequence somewhere in there. It's just that someone already did it, so. Yeah, like what I did in it was which stream was it? It was the previous stream, I think. What I did there was I took the sequence that Pongo OS had, and I rechecked all the register numbers and added a few that were not there that XNU had register names for, and then I reloaded in Python. and sort of also part of this process is to is designed to add distance, if that makes sense, between the original code and my implementation. Like, I believe the original code, if you look at the other versions for other CPUs in XNU, it's written in assembler, and I'm going to write mine in C. And sort of having gone through Python and through its structure and then back into C and stuff, is part of this is to sort of guarantee that only the meaning, the operations that the code performs have to be the same, because it's just making the CPU work. But other than that, like, there shouldn't be sort of any structural copying from Darwin or anything like that. I should just paste this here, actually. Why Python? Why not Python? I don't know. I like Python. I find it very convenient to do this kind of research in. Yeah, Apple calls these tunables. I mean, I guess that's a fine name and all, but I'm going to call them chicken bits. Well, I'm not going to be using their code for CPU spin up, because that's Linux code, and that's actually not the way it should be done, because in ARM Linux, it's normally the bootloader or the firmware that spins up CPUs, and there is a spin table interface for doing that, which is what I'm going to use. So I'm going to look at their code to see how it works, and then I'm going to write my own mini code and put that in mini. SPI, I don't know. I haven't looked at that driver yet, if it worked. I mean, if it's a reasonable SPI driver, sure, why not? Wi-Fi, they didn't write any Wi-Fi drivers. It's the Broadcom Wi-Fi. They probably made some patches for it, but they didn't write a Wi-Fi driver. SMC, I haven't looked at that. Yeah, like if you... Yeah, so I was saying, like, everything Corellium has written is sort of the easy drivers, right? It's either very small drivers or it's adding support to existing Linux drivers, which is fine, but like, I mean, some of the things they've done make sense, and some of them don't make sense, and the ones that don't make sense, there's not much point in using that code. Like when the code got reviewed on upstream, the way they did FIQs is not the way upstream says they should be done. So I'm going to be looking into that a bit later. I'm interested in their IOMMU code and the Dart stuff. See how that's done. If it's reasonable, then that should be fine to use. Like, SPI and squared-c. If if the drivers are in properly, I don't see why we shouldn't be able to use those. But like, yeah, the sort of the way they did FIQs and CPU spin up and WFI, like the WFI stuff is complete nonsense. There's a bit for making WFI work normally on these CPUs, as far as I can tell. So I'm going to try using that and sending it here in Mini, because Linux doesn't need to care about that. And in principle, if I'm not mistaken, by only writing Mini code today and changing there's two things. Only writing Mini code, changing the device tree for Linux, and one thing, adding IPI support to the ASC driver. With only those changes, I should be able to get SMP support in Linux without anything else, which is the right way to do it, because you want as much junk in the bootloader, and Linux shouldn't have to care about any of this. So yeah, that should be fine. I think that's standard. And we're just going to call these that, because we can then rename them afterwards. And also this way I can sort them, which might reveal interesting things, possibly. What do you mean by this doesn't need to be done, but for new features it needs to be? What do you mean with that question? Oh, you mean asking like RFC? It's not a requirement. RFC is just sort of as far as I understand, it's just a sort of a polite way of saying this is not necessarily a upstream submission, but sort of let me know what you think first. And I mean, I'm not like, is that even document? I think it's just sort of yeah, like, I mean, it's just implied, right? But I don't even know if it's officially in the documentation anywhere. I've seen it before, though. Yeah, I don't think that's even official. Yeah. Is it in there? Can't type today. This one? Yes. Yeah, it's just... Yeah, it's... I think the meaning of RFC is just... I do not expect this to be merged in its current form, but I mean, calling it a V1 also doesn't mean that you expect it to be merged in its current form. So, this actually, was that an official one? I forget. No, that's only Apple too. So I do need that one. 3, 6, 15, 12, 4. What is APSDS? Is that just the pack thing? It's under the pack thing, actually, yeah. Key build. You know, we might not even need any of that. Like, that's the thing, is like, you know, these HID bits and whatever this is, which looks like this actually looks like a bunch of attributes to me. Like, I look at this and it looks like 8 bits per attribute. It just looks like a table, basically. And like all this stuff. This is these are the real chicken bits, right? But then there's also things in here like this ACTLR and APSTS. Actually, yeah. Like, what is that doing? Hold on, let me look at the... Because that's the other thing, is anything inside here that we can explain, that's a lot more valuable than just having a list of registers. For example, we already know that some of these bits can be used to make WFI do the right thing. So there's actually a 4 stop in there somewhere. Yeah, this thing, right? So that's actually an interesting one in these two. And let's see what else is in there. Yeah, so it's actually, I'm going to look at all these files and see if I find anything interesting. It's APCTL EL1. S34C1504. Wait, 341504? That's MIGSTS here. 341504, yeah. Uh-huh. This is old, but hold on. Okay, so STS literally is about migration. That's interesting though, because wasn't that the old, yeah, these, right? H9. So hold on. See, in this Apple core generation, it used core level switching. So you migrated code from one of the cores to the other, like atomically. That's not the case anymore. The cores all run in parallel, so migration shouldn't be a thing anymore. It's just normal, like, core switching in Linux. So yeah, STFU is just that, by the way. Everyone asks about that. Yeah, okay, so actually this doesn't make a lot of sense. MIGSTS became APCTL, didn't it? Hold on. This might be a bad name. See, that's the thing, is we want to make sure... See, this is under Apple Monsoon, right? And then... Yeah. There's a bunch of stuff here. Like, the HID ones are all generic. But Typhoon and Twister are the old ones. And, like, these... Hold on for a second. See, this is the thing, is like, you know, some of these names came from the original code I saw, and they might not be correct for the CPU. Cyclone, Typhoon, Twister. Yeah, so these are the old ones, pre-multi. Actually, this is Cyclone, Typhoon, Twister, and this is only Typhoon, Twister, and like Cyclone is out. So these are for the old ones, and then it's called ACC override. So 60 should be 351560. Yeah, it's not Cyclone anymore. So what about this one? Yeah, it's ACC config, right? So has BP red. What is that? It's not defined anywhere, but the code might tell me something about it. Oh, branch target retention, branch direction detention. Oh, I see. See, documenting all this stuff is important. Branch direction retention stability. Yeah. Okay. BP, yeah. Okay, so branch across ACC sleep. Yes. Yeah, I have the code names here. The Cyclone. Like, that's why I wrote this table, because it was freaking hard to find all this information online. It's spread in a million different places. It's a pain. I just wanted one table with all the names, especially for this stuff, for the CPU core stuff. Okay, so we're gonna need a wiki page about this eventually. So I'm gonna start writing that now. What are these called anyway? I call them MSRs because the instruction is MSR, and I think in x86, but in ARM32 there were coprocessor registers, and it seems ARM64 is doing a weird thing where they mix instruction encodings for like non-argument operations and read and write operations, and they all use this kind of syntax with C15, 16. What does Apple call them? Just system registers? What does Linux call them, actually? I think Linux just calls them system registers. Yeah, probably. Yeah. Oh, we're gonna need to mess with this one too, the CPU feature stuff, probably. Yeah, let's just call them system registers. And they were vendor defined, if I remember correctly. Apple ARM system registers. Not Apple, sorry. Wrong button. Yeah, implementation defined system registers and S3. In principle, S3 everything is implementation defined, right? But then, like, all of these are implementation defined anyway, so what's the point? Like, how does... Oh, wait, CRN is supposed to be 1x11. Okay. which is 15 here, so that's fine. Okay, so all the ones that have 15 in there are supposed to be in implementation defined. Which all these are. Okay. So yeah, I'm going to start writing these things. So yes. Do I want to do a table? I'm tempted to literally just make this code for ease of copying and pasting. But I'm not sure if I want to do it for the wiki. Yeah, the only one I'm going to do is I'm going to call sysreg so we make this the same as Linux. Someone just pinged me. Yeah, so someone just asked me in IRC, but I guess I should mention this publicly anyway. If it's worth disassembling Darwin to sort of more deeply investigate this stuff, I don't think so. And the reason is that, well, Apple is already upstreaming, not upstreaming, sorry, but is already open sourcing Darwin normally. And even though they kind of censor some of the iOS CPU stuff, a lot of the stuff is still in there, right? So I would expect them to release a version of Darwin with the M1 stuff in it pretty soon. Well, I mean, I don't know what their timeline is for open sourcing this stuff, but I expect them to eventually do it. So it's not worth disassembling Darwin. Like, we need this specific sequence to make anything work, but it's not worth disassembling Darwin to do deeper reverse engineering into these registers. We might as well just wait. Like, basically my plan here is I'm going to use just this sequence, which we absolutely need, and published open source versions of Darwin, and get as much information as I can from that. And I'm sure they will eventually release something that has at least names for these things anyway. But yes, so what I wanted to do is, well, I guess we might as well call it like Apple does. So yes, I'm gonna just make this code copy and pasteable into Linux for practical reasons, even though we're not gonna actually use most of these defines. Some of them we might, and this way they are nice and useful. So, but some of these will have to change eventually. And because this is I think most of these will be related between different CPU generations anyways, so we probably don't have to break up the wiki page at this point, but we might eventually. Depends on how things evolve. I don't think these leftovers are literally from PowerPC. It's more like they're just giving some homage to to PowerPC conventions. Apple does a lot of that. Like their IOMMU is called Dart, which is also an Apple PowerPC thing. Ah, thank you. Windows mentions that S3 is system registers, 2 is debug registers, 1 is system operation. And, okay. That makes some sense. Yeah, I know about the encoding. Like I already have that in my in here, right? In my utils thing, where I can do that. Yeah, but I kind of I mean, the thing is, if you think about the target platform for these CPUs, it's very different from what they were doing with PowerPC, and it's so many years later that, I mean, I guess it's possible that some stuff literally came from the PowerPC era, but I think it's more likely that just the people came from the PowerPC era and started calling things after PowerPC names. I wouldn't assume that there's anything directly descending from PowerPC in these CPUs. No, they made low power ISA chips for many applications. I didn't know that. That's kind of interesting. I don't know. What's the timing for that? Were they doing that when Apple bought them? Anyway, this is all speculation, and not the CPU kind. Interesting. There could be something from that then. I wonder. The only PowerPC that I know is the IBM implementations, so especially 750 for obvious reasons. Okay. Given that timeline, it does make sense. They shipped those in 2007, they bought them in 2008. Yeah, okay. In that case, I guess it is possible that that these CPUs include something more directly descending from the power efficient chips. Interesting. All right, so we got this. This reg E-hit 4, E-hit 20, E-hit 10, E-hit 11. Why is it E-hit 20? I think it. I guess I started encoding the 20s like that. This encoding is a little bit weird. I guess that should be down here, but then why is it E hit 20? Where is hit 20? Let's see. Yeah, see, there's no hit 20 anywhere, is there? No. And yeah, so these are interesting because these are basically saying, let's see. So I definitely want to copy that with the bits. What is ACC, I wonder? It's probably something about core cluster or something like that. Apple core cluster. Yeah, the RCL bug is fixed. The EART driver is all fixed now. The EART works great now. I had some of the wrong IRQ bits, that's why I was confused. What I thought was receive interrupt was actually autobaud. And that kind of makes sense, because that will trigger before the character is fully received, and I confuse everything. I wonder if ACC is mentioned anywhere in here. Oh, CTRR is also an ACC. Interesting. I just realized the two nibbles for H10 are in there, and that's... Which ones? Where does it go? It goes up to H12, which is pretty close to this, so... It'll be interesting to see if any of these also match anything in... Upper core complex, yeah, that could be something like that. Also, that goes up to HID 16. And that is interesting. So that is 16. I'm just going to write all the registers here, because at this point I want to be exhaustive in documenting everything, even if they're not... Wait, what's this numbering system? 17 is 3, 0, 15, 15, 5? Like, all these make sense, right? And then you get here, and this doesn't make any sense. So E hit 11 is 1, yeah. And then we got 13. But that's already weird. What happened there? It's like they got to 11, and then someone did something stupid, and they said, "Oh fuck it," and then after that, nothing makes sense. Like, I assume hit 15 is that, but I don't know. It's just... this is going on the wiki anyway. I'm just going to save it for now, just in case. And then 18 is 11-2? What? This doesn't make any sense. And then 21 is 1-3? What? Like, this really doesn't make any sense. Yeah, so these HID bits are not per CPU generation, which makes me think I like this, like, enable fix bug, enable fix bug. This is great. I'm guessing also that some of these are literally just literally spare register bits, right? Like in the silicon, they are bits that are not connected to anything. But then they realized they had a bug, and so one of the things you can do in silicon is, like, if you have spare logic that is not used, you can change like only 1 or 2 metal layers and fix something. So like these spare bits are that, right? They're literally just bits that don't do anything until they realize they have a silicon bug, and they can like run a wire to that bit and fix it. it's interesting because when you do, like, in a way, I've never done this myself, but I guess when you are doing silicon patches like that, in a very real way, you're reverse engineering your own silicon design, right? Like when you do silicon design, it's all high level, and then there's like low level place, like there's like, you know, blockwise placement on the silicon, but unless you're looking at like a really critical path or something, no one's looking at the individual gates and transistors inside the silicon, right? That's all compiled, unless it's a manually laid out block. But then when you have a bug and you find a bug in like the Verilog or something, then someone has to go and dig through and figure out how that got synthesized into silicon, and then figure out how you can patch it by patching transistors. So I'm sure that's a fun job. Okay, so are we missing any? We got 0, 1, you got E hit 2 and E hit 1. And these are as expected, I think. Yeah. We've also got E hit 3. Don't need that anymore. E hit 4, hit 5, E hit 5. Yeah, we got E hits for all of these. Hit 6, 7, 8, 9, E hit 9, 10, E hit 10, 11, E hit 11. Yeah, hit 13, hit 14, hit 16, 17, 18, E hit 20. Where's E hit 20? Is that even not... That's like in a different place. Isn't it defined twice? Yeah, it's defined twice. Yeah, they got... I mean, you can definitely get the information out of the synthesis toolchain. You can follow blocks around, and like the net list should be annotated with where different nets came from, but it won't be perfect because just like optimizing compilers mess with your instructions, silicon synthesizers will optimize and do weird things with registers, so it's not necessarily totally obvious. So, okay. So we got the HIDs. Let's look at the other ones. So we got these are the old ones, which you don't care about. Though these are... Hold on. So the HID, yeah, we got those. And the override thing... It's probably AC, yeah, it's ACC override, right? Are these the same? Bit 24, force up, force down. Yeah, so these are actually different. Okay. So I think this one survived the rename. Yeah, has cluster. Yep. Yeah, so this is for the non-retentant WFI, which makes sense. That's for deep sleep kind of stuff. See, one thing is that there should be some there should be cases where this all restarts in the bootloader. And one of the things that I saw is that apparently iBoot will lock down a register that tells the CPUs where to start when coming back from deep sleep. And so Linux needs to recover from that somehow. But I'm thinking, we already have spin tables, so why can't we just keep using spin tables, right? Why can't we just use the exact same protocol that Linux uses to bring up CPUs on initial boot to bring up CPUs on wake from sleep? It's the same damn thing, right? So, yeah, I think this should work. Basically, I don't want to introduce a completely different CPU boot protocol into Linux, because that's going to be one of the because that's what the Kernel guys did. That's going to be one of those things that upstream absolutely hates. So sys acc config, sd config. See, I hate the name because it's so acc override was 560, and this is cyc override. They should have renamed that or something. C1540, yeah. Yeah, no, the most interesting change that we're going to need is the thing about the bus access type. The way Kernel did it is broken. That's not going to work. The reason it's broken is that they unconditionally change it for all accesses in like the mapping registers in the ARM, and that doesn't work for PCI Express. We know that now. But the problem is that Linux doesn't support this. PCI Express drivers and non-PCI Express drivers all use the same function to map I/O memory with no arguments. And so, a priori, there's literally no way of implementing this in Linux without some kind of core change. One ugly way of doing it is to try to do it by like memory ranges, like figuring out which address you are in, and if it's PCI Express, then do a different thing. But that's a hack, and hacks don't go over well in Linux. So I actually spoke to some of the maintainers, and one approach that actually makes a lot more sense is to actually do a tree-wide cleanup in Linux and make PCI drivers all use a different function. Because, it's open. This is why Linux is open source, because it means you can actually maintain all the drivers, and there's no binary compatibility. So you can just go in, and if there are 600 drivers that need changing, then you just change 600 drivers. That's something you have to do carefully, but it's an option, right? And so there's, not wanting to do that is not a reason to do things in a hackier way. And so that's the approach that I'm going to try once I get this far, is introduce a PCI IO remap function that by default does the same thing as IO remap, and then make it do something different on ARM64 if you're running on an Apple platform. And I mean, this might or might not be the way it ends up being done in upstream, but it's the kind of thing that has to be tried to see how it would look and if it makes sense. So, and I could totally see on certain platforms, like PCI tends to be special, I could totally see this being useful in the future on other architectures or other weird chips. So it might even increase performance, right? It might be that on some platforms you can change the access type on PCI and get better performance or something like that. So, so yeah, that could be interesting. The Corellian approach doesn't work. They unconditionally change the mappings in the CPU register configs to make it to basically fake one type into being the other type. So everything goes through the NGRNE, so the one that works for IMV, but that doesn't work for PCI. So the Corellian patch is broken for PCI, and that's never going to work because you need the distinction before you get to that stage, right? Once you get to that stage, there's no distinction between PCI and not PCI. I didn't know anything about ARM64 when I started working on this, and I'm still doing it. But that's the thing, is the code's there. Just go read it. Well, NG and RNE, those are memory access attributes, and that's basically ARM making things complicated for people. NG and RNE means non-posted writes. NGNRE means posted writes. And then the other types are less strict. There are access types that allow, like PowerPC has a different name for this. What did PowerPC call these? I have that PDF somewhere. Isn't it on my... Didn't we have that in favor of, though? Yeah, that one. Every CPU calls these different things. Well, they probably just did the ugly hack with the address ranges or something, right? Like, we've already established that they are not talking to anyone developing Linux. So, I mean, like, it's not about getting it to work. It's about it's about doing it in a way that is upstreamable and maintainable and proper, right? So, so yeah, like the way PowerPC calls this is, if I can find things, yeah. So it has these RNC bits, and then there was this the ordering thing was called. Where was that stuff? Because it's nice, sort of mapping these things from one CPU to another, so we get an idea of where is that running model register set. So here's the HID stuff in PowerPC, right? I think one of them was called guarded in yeah, guarded storage, right? So that's one of the things. Memory protection. Yeah, so there's cacheability and guarded stuff. This is the thing, right? The WIMG bits. Yep. Let's search for WIMG. $297. Yeah, this south, right? So no, not quite. Yeah, so it even has a Wikipedia page. Yep. So this is about the cache, and then it's got memory coherence and guarded writes, right? So basically guarded writes are the NR in, and I don't think PowerPC has a specific thing for posted and non-posted, but basically the NGNRNE. So re is write gathering, R is reordering, and E is I forget, it's like end to end, but basically early ACK or whatever it was called. And so in PCI terminology, this means non-posted, and this is a posted write. And like GRE would basically be not guarded in PowerPC, effectively. And then there's also the caching stuff, which is separate. So the different levels are basically NG, RE, I think, and then GRE. I think these are the ones that make sense, right? And so this can be reordering allowed. And this is basically, at this point, almost cached. Like, once you're at GRE, I can't really think of many cases where you'd want to use GRE and not just turn on the cache. Because it'd probably be faster to just turn on the cache and just flush once you've done with writing whatever you're writing. But yeah, that's basically the story here. Anyway, back to the register. So I'm going to, again, document some of this stuff. So we got these so far. And the thing I don't know is if all these HID bits are really for all Apple ARM CPU cores, or if they're only used for some cores. I'm not sure. But the way they've defined them here kind of suggests they do, in fact, use them for all cores. Also, what's the CPU doing? Oh, it's just OBS. Okay. All right, so let's just call these. So this is mask is 7, B shift is 60, so 662. I hope I'm guessing these name expansions. Like, hopefully. Should I be writing these? And yeah, I guess I can use LSB first. One BRN. What's BRN? Disable? This B? sure. I guess. So let's see if we find any of those. I was going to write mini code today, but I guess I'm going to end up documenting chicken bits instead. Yes, because all of these are going to have comments anyway, so... LSP. Is a loop buffer a thing? Is this an Apple patent? Are we going into patent searches now? Because that's like a DSP thing, but... Oh, there's a computer architecture buffer class here. Why is this so slow? Yeah, so it's... That makes sense. Cute. Oh, the Cray one used this. Well, that's cute. Neat. So it's basically a decoder cache for tight loops. Oh, Samsung got this patent. But this is some coprocessor things. Neat. Expired? Really? Oh, like as of... Isn't it 20 years? Wait, then it has like... Oh, fee related. So they didn't pay the fee or something? I don't know. Yeah, anyway. That's not even used anywhere. Yeah, a lot of these aren't used. Oh, there's one for H9. Okay, so what I'm going to do instead is just write these out first, and then go through the tunables pages and like update them with any comments. I'll just might as well use the full names that I'm using here. HID1. CMP. Oh, okay. That makes sense. Force Nex L3 clock on. That's interesting. I don't know why we have so much random L3 stuff in here, though. These are supposed to be CPU chicken bits. This like it's most this looks like it's mostly load store stuff, but then there's AES in there. That's one of the ones that were used earlier in that part of the code. In groups, I guess. So I guess that avoids speculating across DAF. See, that's actually isn't that the EL3 thing? So this could be used to emulate like the existence of an EL3 monitor or something like that. Probably. Well, that's like if it has ECO in the name, engineering change order. I think is what that probably means. You know, it's some deep crap someone had to deal with. 60, maybe. Oh, that's also a spare bit. Lovely. Yeah, I know. DAF are the ARM mask interrupt bits, so I'm wondering if that's basically it should be avoiding speculating across. I guess it's avoiding speculating across an MSR instruction to the interrupt mask bits. Well, AES Fusion in general is just running multiple CPU instructions as one. So, and AES is the encryption instructions. So this has something to do with fusing AES instructions, and I'm guessing that there's probably so there's different so there's one round for encryption decryption, and then you can do the mixed columns and the VML, which is used for the S box, if I'm not mistaken. So probably means that they can run more than one of these in a single round or something, like more than one round in a single cycle or something like that, is my guess. And this disables some of that fusion. Like all of these, almost all of these things are basically going to be saying disable something because it's broken, or something very much along those lines. Oh, also, hold on. There's a different. Really. What's MTB? Something translation buffer? Not sure. All right. Let's close this. Hit 2. Color opt. Oh, that's. I wonder what that is. That sounds like some kind of algorithm. Wonder what that's about. I guess. That's interesting. Like, if you got all these, like, why is PCIe related stuff in a CPU register? Like, it makes you wonder exactly where these bits go, right? Like, how much stuff is integrated into the core complex that has to do with PCIe? Because these bits are supposed to be per core, right? I think, unless some of these aren't, and which would be interesting. This is the same thing, isn't it? So now I kind of don't get this E-hit thing, where some of them are the same bits anyway. Let's see. L launch? What's... Not sure what Lynch is. This is getting deep into disable non-speculative ordered load request, no order, something like that, but it's very hard to make a good guess. Guess. Where am I? It's mask is 3, so LFSR? Probably not what I think about when I think LFSR. And then somehow we went back to bit 9 here. Yeah, which is why I have this code, right? This is the XNU code. This is descendant from the XNU code that makes everything work. And without this, Linux doesn't work. We already established that last week. But the thing is, other than this, well, first of all, we want to understand as much as we can about this initialization in case we want to, for some reason, change something. But more than that, for example, we know this CYC config stuff changes the WFI behavior, and we want to change that for Linux. But more than that, this might let us discover workarounds for other issues that don't affect macOS and affect Linux for some reason, or we might decide that we don't need some of them or something like. You want to start with a known good config that is what Darwin uses, but that doesn't mean you can't go around and try flipping bits and see if something is useful. So that's why I want to document this. And now we're back to out of order bits. That's the thing about vendor code, right? The Linux coding standards tend to be better than most vendors. Things like having the bits in a random order like this wouldn't usually fly for most reviewers anyway. I guess. And then we have 14, and it should be whatever that is. Uh, 35. I think they use ehit normally in the chicken bits and stuff, so it doesn't make sense that it would be for an emulator. I think it just means extended. We've got and this is 5 bits. No, wait, clock div? Did I clock or... I'm actually not sure if that's clock divider or like division unit clock, so I'm going to call it clock div. Interesting. This is 20, which is before that. whatever that is. Spec flash pointer. Disable can type. It's yeah, so this is some kind of table again. Sorry. It's not 60, 56, sorry. It should be 7, 4, and 11, 8, and 59, 56. And then we have 63, 60, 93. Okay. So see, this is interesting, for example, right? TSO allow DC Xavier diversity. TSO is that x86 simulation mode stuff. So this is potentially relevant. Sorry, to clarify, TSO is the bit that enables the memory order that is useful for x86 simulation. And also TSO enable is right here, right? That's the magic bit that we need to actually use in Linux to export that to QEMU so that it can get the so that it can use it. And so these things are potentially relevant to however QEMU's JIT works. What do you mean by not all of these are defined in this sort file in XNU? This is XNU. And these are great. If these enable fix bugs, then shouldn't we just turn all of them on? Like, now I'm wondering if these are like Rosetta things. Because this entire register seems to be very much related to TSO. And yeah. Oh yeah. You're right. Yeah. I know there's some of these registers are in some other places. That's why I opened more than one. Like this is procrec thing too, right? So. I do wonder what they mean by widget. Like, is that like maybe it's like a microcode thing or something like that? Sorry, that's 54. performance, maybe? I think WSD probably means wait state. And these are for Typhoon and Twister, else... Oh wow, they even freaking... Are you kidding me? Come on. And then 13... They even... And Typhoon and Twister were... Oh, those are the old ones, we don't care about those. Disable fast string optimization. Yeah, I think a lot of these probably only for specific CPUs too. But we don't know which ones, so... And some of them might still work on newer CPUs, even though... Like, for example, you set the chicken bit to disable a broken feature on an older CPU, and then you don't set it on a new one, but the bit's still there in case you need to do it, for example, right? That would make sense. And this should be 41. I should make a note here of that. That's a lot of... That's at least probably 12 bits. And CUSD is that Cyclone, right? I don't remember if Markdown lets me do this. I probably need to put a space in there later. Aggregation, aggressive, probably aggressive, but whatever that is. I hope so. We'll find out later. What are these? Some of these are completely incomprehensible. Okay. And like Linux has these things too, right? If you look for that's a nice disk. Yeah, but like yeah, here we go. Like especially the GPUs, right? If you look, like Intel has these literally, they call the registers chicken. And you need to set a ton of them to make Intel GPUs work. There's a whole Intel workarounds.c. But not just Intel, right? AMD also has a whole bunch of chicken bit registers. Also, they also call them chicken bits. And then like Intel Wi-Fi apparently also has chicken bits, and QLogic NICs apparently also have chicken bits. And these are just the ones that people actually call chicken bits, but I guarantee there's a whole bunch of this kind of code in the kernel. They just don't call them chicken bits. Or something. Let's do this compile. Transaction probably. Okay, and now we finally are done with the hit bits. So that's C61. I wonder, like, this is the 3 means deep sleep. No, it's different on some of them. I'm gonna have to order some chicken too, am I not? I think my lunch today is going to be Korean chicken. Train down link, maybe? I'll have to look at that later, but so look at this. Like, this is basically saying under which circumstances is the hardware allowed to turn certain bits on and off. Whatever DTR is. Did you have that one too? Yeah, we did. Well, that's interesting, right? So that might be whether a core that powers down and then powers back up in full deep sleep, whether it returns after WFI or whether it returns in the like the exception vector thing that iBoot says. That's also interesting because if we make it return on WFI, because I think there's a way of preserving at least the program counter, then we don't have to deal with jumping through the bootloader and the spin table for all that stuff. So again, this is all stuff that makes a lot of sense to investigate. And this is going to be at least there. So this is the magic WFI, mode thing, if I remember correctly. So I guess that's whether it wakes up on FIQs and IRQs, which is also going to be quite useful. 23, 22. I should just I'm going to rename this work stream because it's not working on Mini anymore. It's all going to be about chicken bits, isn't it? Because I'm definitely not going to get anything else done other than the chicken bits before I have to stop to get some food. So this is now officially a chicken bits work stream. No, this is going on GitHub. We use Hugo for the website, but we don't have any documentation on the website yet. I haven't figured out yet in the long term how we will be publishing documentation. But right now, our docs are on GitHub wiki, and that's where this is going to get pasted. Actually, I should be renaming this as Yeah, that's more. That's nicer. Something like that. Actually, not sure if those brackets will confuse GitHub or not. We'll find out, I guess. And then on Monsoon, there's a DSVL Snoop time, but I guess that's Monsoon is quite a while back. I think we don't care. And then these are... So STS... So these are, I guess, error information registers or something like that. But then it's also what do you do with errors. Error control, but then error STS is, I guess, status. Do I have these in here yet? No. Okay, let's put these in there now that we're done. So we've got L2C error STS is 8, C9 is L2C error address. Inf is information. Whatever that is. I'm gonna need more to tab everything else more, I might not. I am a kernel contributor. I have patches in Linux already. Not many, but I have some. I've had them for many years now. I sent one last year, actually. A couple of them, actually. If you use one of those little Chinese USB capture cards, like the $15 ones, you may note that those give you stereo audio only on Linux, not on Windows or Mac. That's because I sent the patch to fix that, because they are non-standard and kind of broken. But also a couple other things. I've got some. Actually, most of my patches on Linux are audio related. Fixing audio on my old laptop, adding support for a DJ controller, those things for the capture cards, mixer fix to a Tascam interface driver. What else? I did fix a battery current reporting issue in my old laptop. There was something else too. Oh yeah, IOMMU fix for the like a workaround for an issue with what's the brand for these things? The J-Micron firmware controllers. Probably some other things too. And there's also some PS3 Linux patches in there, which were actually upstreamed. So 341501 is actually this, which is not H13, it's and then we got 05. Oh, this is 5, sorry. Wait, hold on. Oh, in here, okay. Wait, this is 415, this is 5. That's weird, but okay. Okay, back to the beginning on here. We've got... $315.00. Hold on. these in order. So 2 is the 15.1 is LSU error control. And then we have 4.15.00. Yeah, so these go in there in order, and then 4.15. So hold on, was that the same? No, did I just copy paste that wrong? 10 is, oh sorry, I was copying and pasting that, wasn't I? 04. Yeah. So 4.15.00 is, I wonder what FED is. This E thing seems to be, maybe it's for the efficiency cores. Interesting that we have the EL1 naming here, but only in this register. And then we don't know what these are. But they are used in the, so these are added basically in for EM1, and we don't know what they are yet. And then we have KTRRs in here, which we might as well also add. 3, 4, 15, 2, 3. And these are 3, 4, 15, 2. Okay, so these are here. T 4, 15, 2, 3. Upper. 4. 2, 3, 4. And then CTRR. Which are the same thing, aren't they? So wait, which ones? When was the CTRR versus? This changed at some point. Yeah, there's 2 of them, right? And why does this laptop like randomly decide to eat CPU for breakfast? It's mostly Firefox. Custom stuff, but I'm not sure what's going on here. Yeah, I don't know. Yeah, I think it's just the usual. I mean, it's Intel, what do you expect? So defines here. Yeah, actually, I just remind myself of when these were introduced. Like this kernel text read-only register and configurable text read-only register, and I guess CTRR is the evolution of KTRR, but what CPU did that get introduced in? This has H9 as KTRR, and for both. Ooh. Program unlock CTR if this CPU is non-boot cluster master. That's interesting. Boot cluster will be like the machine lock them. Oh, okay. So maybe that's how this works. Maybe these are not global, but they're per CPU cluster. And so so like the boot CPU in the non-boot cluster has to do some extra things. That's interesting. Okay. That's good to know that we have a hierarchy here. So we're going to have to do some global things, some per cluster things, and some per CPU things. Mm-hmm. Interesting. Yeah, none of this is properly documented. I think APRR is not the same thing. User JIT index. Mm-hmm. What is that actually? 341512. Ah, yeah, that's not in there. One is in there though. Oh, these are the IPIs. Yeah, we need those actually later. The kernel key stuff there. Ah, there we go. VMCA lock. Yep. Those are the ones that this is talking about. Anyway, okay. So moving back to this. LSU error control. FED error control. MMU error stats. You need that one. 61502. 00 and 20. And then we got 158090. Then we only have those? Yeah. No, it's 63. Okay, yeah. And then we got that one, SDS, and 51505. DPC. Yeah, we got those. Cool. Okay, so that's all of those. and that should actually go in here. All right, then KTRRs 341523 2422, yeah. And then CTRR 341523. Well, these should be CTRR if I'm remember. This should be a newer CPU anyway, so. Lock, and then we got TRR. A lower is 3. Before 1524, yep. And then let's control EL1 and 25. And then there's ACC, which is interesting. EL2. Why are those called ACC and not just ARM64? Well, what's going on here? That doesn't make a lot of sense. It just should be the EL2 ones, right? I think their naming is just inconsistent. And the numbers are different too. Lock EL2 is 5. And control EL2 is 4. And then lower is 0 and upper is 1. Okay. And then we have these control. Yeah, these are the bits. We'll go through the bits later. Actually, no, let's put them in here now. We can go back to and cover these first. STS 54. Not error, so oh, it's the same. Sorry. STS and CTS. It's the same thing. I guess that needs to go in both. And then hopefully it's the same. I'm going to call it EL1. Where are the P registers anyway? This is probably like page execute never, and U and P might be from like protected and user mode or something like that. But where are the B? We don't have the B registers. Yeah, we only have the A ones. Maybe the B ones are locked by the bootloader and we don't use them here or something. Objective-C branch predictor? What do you mean by the Objective-C branch predictor? Yeah, these are... Yeah, execute never. Yeah, unprivileged execute never, unprivileged execute never. Yeah, it's what I expected. Okay, so now we have the... Need to add them here first. 351501. Zero and 01. And we have a cluster anyway, so... Wait, did I miss something? Did I DBC RSTS now 1505? 351505. Yeah, it is there. I hate the numbering here, because I want to keep this sorted, just so I don't miss like duplicates or things like that, but it's kind of annoying. G51511 and CR1531. And then suddenly we have what is has next PG? It's not defined anywhere. But this is for set next PG, next power gating. Interesting. Did we only have that before? Did 13. Oh, that's also in here. Okay, so this is just in hit 13, which is defined twice, isn't it? Yeah. Lovely. And PG should just be power gating, I guess. This is so this is 6360. And then we have a 14, which hopefully is also the same as before. Yeah. 32. No, the source code for Linux for XNUON1 is not released. That's why this is all partially guesswork based on previous CPUs and why some things don't have names. E hit 20. 1512, yeah, that's correct. And then one. And this is 22, 21. 16/4 non-speculative if spec slash pointer look return or something. Didn't we have a trapezoidal MC earlier? Yeah, that's in hit 1 and it's also in hit 20. Maybe it's for the E. And then finally, let's call this non-speculation. So if oldest GRV, LD, and older, whatever that is. Okay. This is the BP retain thing. And that is 351540. Which is easy config. And we need 2 of those here anyway, but we've got 2. It's just 1 really. Sorry, BTP, DPBTP. So how does that document it? Let me read that again, because these were interesting. Yeah. Or not. PB something. Yeah, those. Huh? That just ends. Oh, it sets the whole thing. Okay, so it set BP red, yeah. So this is a branch predictor. So S14, this loads from BP red. What is BP red? 3. Okay. And now pack. 341504. Wait, what? Oh, come on. Really? That's annoying. But MIG STS should be for the old CPUs that didn't have packs, so... but this is annoying. APSTS. One zero. Wait, 3 6 15. 15 12 4. Well, that's already there. Okay. And then there's API key. No, yeah. It's 302. Wait, this is not a vendor-specific register. Uh-huh. These are not Apple-specific. So I guess probably the control registers are Apple specific, but the actual, and the kernel keys are Apple specific, but the actual... But I guess I'll include them for actually, you know what? I'm not going to include these. These are the same. Yeah, there's too much junk here. We only need the kernel ones. I'm not going to include these. Okay, and then we have the MCA lock 3 4 15 1 2. And I think we're out of it. Yeah, we're out of registers. So let's go back to documenting bits. We did all the hid ones. We did these, I believe, the override. Yeah, we did. You don't care about monsoon. IPI registers. This is IPI RR, global and local should be the same. I think SR and CR are probably just like set and clear. Yeah. And that actually writes the CPU ID. Interesting. That is... Yeah, so what we have here is... Let's do them separately. Which makes sense. So what we have is, this is for signaling CPUs in the same cluster, and this is CPUs in a different cluster, so I guess this is faster than this, and they're implemented differently. After that, what we have is... An ACC does sound like Apple Core cluster or something like that. Oh, interesting. CR... Oh, okay. Interesting. So this is the countdown. And it's literally just a... Aha, so this is actually... It says it's a global register where there are two copies. Aha, it updates both copies. Interesting. Traverses both rings. So now we know how this works inside the CPU. There's a ring of operations basically that goes around and it gets parsed and interesting. Well, for software purposes, it's a global register. Oh, interesting. So wait. Oh, okay. It puts it in a global. Cool. There's a lot of stuff here anyway. Oh, but this stuff, yeah, it has to do with the, pointer auth things. Anyway, so CR is just the countdown, and the other one we're missing is the IPI SR, which is probably for Axe. Yeah. It reads SR if it's one, it's an IPI. Yep, status register, right, if it's an IPI. And then it has to just write the same thing. Yep. And we need the barrier because otherwise it might start running the handler and the IPI isn't act yet, which means it would get act late. Yeah, that's what it, so yeah, okay. So in that case, we need okay. I think that AIC probably should do the same thing and make sure that should have a barrier in there for. Though, wait, does AIC need a barrier? Yeah, because of speculation. What exactly was ISBSMI? What kind of barrier? Yeah, full system. Yep. All right. Where were we? Next PD. We had those already in here. And the 20 and BP ret, we need those. Oh, we have those. These are an ACC CFG. Yeah, we have those already. And then we have the pack stuff. Why am I using these as 3 anyway? Might change that to 2 later. Okay. P-core, not E-core. So this is the regular thing. Yeah. And that's bit 16. Affinity level 2, yeah. Ah, I see. So this is... okay, so this is... using 2 different MSRs. These used anywhere? Just in a couple places. Ah, okay, so E hit, so E means efficiency, and yeah, definitely, and the other one means performance. For now, we're gonna call them this. Yeah, there's some stuff in here. Oh, interesting. It also does... Okay, so E hit 4 and hit 4 should basically be the... This is like CPU bring up stuff, right? Go on start, yeah. The hell is that? Oh, it's the pointer thing. Ah, and there's actually an Apple mode. So maybe we can just ignore all of this, and it will support standard ARM pointer authentication. Probably, yeah. Where is that defined? Where is that? Oh, pack has them, I see. No. Procreg. Oh, there's more stuff here. But this is probably also all the... Yeah, it's going to be all the... Well, we should document the ID registers anyway. Heart num is 15.4. Forgetting these things. Should probably need these. We'll find out about the new ones. And that's 38. And we have the code names, which we can fit in. PG is 87p. You're right. Off by 1. These might be useful. Is that standard? Yeah. It's not standard that it's standard that it's not standard. But we don't have those anyway, so. Interesting, there's some actually useful docs there. But it's not actually used anywhere, so. It says debug stuff. And APR was also an Apple thing, right? Or it wasn't. Hold on. Yeah. Or not. Huh. Why are those like nowhere? Well, we know the names. G4 1522, G4 1520, and 1 is here 1, okay. And then we have 6 and 7. This doesn't talk about the actual registers, does it? Anyway, we can look at that later. The things are here anyway. So what's sys? We get sys. Where do we get that? Oh, yeah, we do want sys. Sorry. Yeah, this is one of those things. Hold on. That should be good enough for that. And let's see. What other interesting things do we have here? There's also XPRR apparently. This should be standard, hopefully. Yeah. But these aren't. You'd think this would be in, like, if it's not in here, it would have to be in the assembler or something. But anyway. Da, 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 da. So here's some interesting stuff anyway. And these are like for the Cortex, which is going to be different. So hold on. Or some of them aren't. Okay, so some of these are in fact defined. Let's make sure I get the latest version. Yeah, so this is standard. Yep. This is standard stuff. ARM64 to unify with ARM. Nice. This tells us about the affinity stuff. It's 8 bits, so 23. F1 is cluster ID. Okay, so that's that. What else is left? Some of the pointer auth thing. Was it AP? Yeah, APSTS. What is that thing? APR EL0. Yeah, we have those. What was the one we were missing there? APCFG, yeah. So APSTS is supported on the newest ones, and that should be all that matters. Yeah, so maybe we don't care about this. Maybe it's fine. So do we have that? Yeah. That's the authentication stuff. Yeah, that should be fine. And then there's some other stuff here. What's ACTLR? That's standard. Yeah, that's standard, non-standard, right? Yep. Okay. ACTLR EL1, standard, yep. Cool. And so the other things I wanted to look at is there's some hit stuff in here that we probably care about. Not this one, that's some hurricane thing. But these are general. This is done for everything, apparently. Which is probably a good idea. And then there's some lightning stuff. And then this is where it does all the this is applied chicken bits, right? And then it's doing a must identify, yeah. So we need a bunch of those. So we need to do something like this, right? So we need probably these things, the hid for stuff. So let's write those from here. And now also let's look and see if I found any of these. 3, 4, 15, 1, 4. I did find that. No, I didn't. 5, 0. Yeah. No. Oh, it is here. Yeah, with our name. Also, it's sorted wrong. And then 3, 6, 15, 1, 0. Yeah, also not here. Okay. Yeah, these look like MMU related things. is P-core actually. No, actually, because E-core is something like that. If that is set, then it's a P-core, so it's not an E-core. Okay. I should just do it like this. And now look at that stuff here. Yeah, so this disables DCMVA and DCSWL2Y. That's interesting. No equals here. DCSWL2. That one, 44. Just double check that. Yeah, 44. And also that DCS, yeah. And before that, it's just the pointer key stuff. This is the pointer auth thing, right? But it's polling APCTL EL1. And then the actual tunables. Where was that? Yeah. These are not looping or anything. Thing is, these aren't doing any loops or anything. This kind of bugs me. So wait for M key valid, APSTSEL1. Wait. Hold on. This pulls. Oh, okay. Pulls APSTSEL1, M key valid. Yeah, okay. So it waits for that, and then what were we having the rest of the... We had more junk in here. Because we don't need the pointer authentication stuff, so... Turns on Apple mode, whatever, that enables the keys. Yeah, we shouldn't need that. Because we don't use the pointer authentication stuff anyway. So it does that, and then it says the migration, but that wasn't migration status. That was the thing with the two names. It's APCTL, that's what that's doing. I knew this was dumb. This is the pointer authentication stuff. We don't need this. Something was yeah, okay. That makes more sense. That part of the code is just this part of the code. This is just this. Yeah, it says user key in, Apple mode, and current key in, and then waits for mkey valid, or whatever. Yeah, we don't need any of this. And that's wrong. It's pointer authentication stuff. Okay, I'm gonna get rid of that now. We don't care about pointer auth right now. We'll worry about that if we ever care about it. Actually, I should not have committed that with this junk in there. I was not expecting that. Hold on. I might just rebase a bit later and get rid of that, because this is mostly my stuff. Yeah, the chicken stuff is in there. I'm going to... This is not supposed to be committed anyway. I'm going to get rid of this, because we know what it is anyway. Yeah, and that can go away. I'm going to rebase, and whoever is has a clone can deal with it. Also, I forgot to sign that off anyway, so... right. The config.h1 does not have it. Okay. Sorry, force pushing. Actually, did I just feel something there? Hold on. Because I think I might have merged some things since then. No, origin main is on there. Yeah, that was pushed. Where did I just go here? Wait, hold on. I just did something weird with Git. It should be, sorry. Yeah, that's fine. Yeah, that's fine. Wait, where'd the move go? That should be fine. Yeah, that's better. Yeah, this is fine. Okay. Okay, back to this. And so in the C version, we do that, which is that bit, isn't it? Bit 11, yeah, and that one. And then after that, we deal with all the other CPUs. So we need this, whatever this is. Is OSLR done anywhere in here? Yeah, it's done in start.s. Yeah, we also don't necessarily care about that. Is that even in Linux? Well, whatever. So that should also probably be in here. See, I'm very curious about what this is, because it's before the pointer authentication stuff in here. So it's something they added, unless I missed something here. Key valid, yeah. Here's that. Oh, is this what it is? Hold on. Ethereal. It's different, but it kind of looks like one of these things. It's a bunch of attributes, a bunch of 8-bit attributes, which looks a lot like this. And sorry. This really looks like an MAIR setting, and it's in the right place in the code, but why is the register completely different? Oh, wait. Oh, no, it's just the misr, okay. See, now I kind of want to disassemble Darwin myself and see if this really is what the code I got, because it looks weird. Like, this doesn't quite look right. Well, this start stuff is what gets put in the beginning, I believe. So we can probably just... I don't really want to load the entire kernel cache into Ghidra, but if I can just dump those things into the disassembler, it should be fine. I'm going to do a quick look and see what Darwin has for that, because I am starting not to trust this code. Yeah, here's a kernel cache. That's from macOS. And I can probably just cut that off. Yeah, so that's the entry point is here. And the that's the beginning of text, I believe. Yeah. So the offset should be C04528 as the, and it should probably start there. Yep. Let's do C04. Yep, as expected, those are vectors, and this should be most of the init code, if I'm not mistaken. So I need the is it -I or format? And then architecture for that. Yeah, that might work. Yeah, this stuff, right? So there's the MAIR thing there, which we were talking about. And then the hit stuff starts here, probably. So 15.4.0.4.1. Yeah, this is hit 4, right? Yep, that's the hit 4. And supposedly before that, there's something with 3, 6. 1, 6. Yeah, that is in there. But that's where? After writing vbar? Looks like APRREL1. There's been some changes here, but... You know what? I think this is APRR stuff. I think this is APRR stuff because it's in the same part of the code. It's doing the same thing, and we didn't find these definitions anyway. And it writes EL1 and EL0. And then it's poking a different register. Like something to enable these and then do them in... And he's trying to find anywhere anyway. So what is this? APRR EL1 PPL? Oh, it like removes after... Yes, unrestricted is 455444777, yeah. And it removes something and... This is that... It looks like a different version of APRR. Okay, you know what? What if I just get rid of all that? I'm just gonna see if Linux boots without issue with these settings, because I get the feeling we can just not care about that, and that's just some version of APRR. Yeah, got a shell. Looks fine to me. Yeah, I'm just gonna say that that was APRR stuff. Maybe there's a different version of APRR in this CPU. We don't know yet. But that looks a lot like a different version of APRR. 3615.6. And then the 50. So what's that about? We don't know about that one. But it goes before TLYML1 in that part. And it's the same thing. It's like unlocks something and relocks it or something like that. 6. And then what's this one? Yeah, that is something that is getting set with the MPIDR, the lower... Okay, so that gets set with the CPU ID. That's probably something that actually matters. gonna write those there, and then we're not also gonna put that one there. So. And MPIDR was what on this thing? All zeros. Yes, we're in CPU 0, cluster 0, E-core, yeah. Okay, so now we're getting somewhere. So let's look about what CPU we are. Yeah. Huh? Oh, right, that's probably because I rebooted, and yeah. GH 340. That. No, I need to reboot that. Oh, it does work, okay. And now that we're here, so we have part number 22. So it's actually 34. Interesting. And this should be that thing. This should be Ice Storm. This should be the P core. Sorry, the E core. We're gonna guess for now. Okay, so we got the head thing. And then we have head 5, that bit. Uh, 61. Disable fill to see merge. Let's copy and paste this for now and start cleaning here. I got those. Don't need that in the end. Wait, 16? No. There. Do we have panic yet? No. Actually, I can probably kind of just cheat by doing... since this is going to boot eventually on other CPUs, I don't really want to call C code, because this is obviously not re-entrant. But UART put S... Probably that's fine. So not only write from a CPU. When I call this, I'll probably like spin up one CPU at a time, wait for it to be awake, and then do the next one, so we can let the CPU do things with the UART while we're doing that. Where's this UART.h? All right. Is this right? It's rec set. Disable, sorry. Yeah, this is rec set. If I remember correctly. Yeah, rec set. And then we got these things. So, HID 5. Let's get rid of all this stuff anyway. We're going to be using those later. We don't need that. Let's get the wiki. There is an EHID 5, but apparently we are not using EHID 5. Just to double check on that. Oh, this is interesting actually. It's doing... Hold on. So this is the reads hit for... Or is it those things? Yeah. Reads MIDR EL1. Then goes and reads 1550. That's HID 5. So it does that unconditionally also. '61. This is probably also a tunable though, so we can just put it on both, but it's hard to tell. Well, it isn't done in the previous ones anyway, so. Hold on, let's go to the vendor docs. Yeah, this fill 2C merges in H12. So it looks like this is inherited from H12. Then it checks compare with 0. So if it's 0, which means it's an E core. But it should be the same anyway. I mean, we're looking for the definition, so that's 301514.0. Hit 13. Oh, this is the P core. We want the E core first because it compares with the 0. So 458, yeah. Wait, what? Yeah. Yeah, and then it checks for not equal, so it's equal to 0, then it's, yeah. And this is doing 301510.0. Yeah, hit 10. 1, yeah. E hit 10. That should be bit 32. We don't have that, do we? We do. Force wait state drain UC. And then it also sets the other one, which is whatever that is. Nah. 49, which is not. It is, yeah. ZVA temporal TSI. That's not even there. You know, I'm starting to think that we might actually have, because this is the 1101 source code, right? This supports M1 because 1101 supports M1, but they got rid of all the M1 bits. But that doesn't mean they got rid of all the bit definitions in the ARM64 registers. So I bet we have. I bet we have. What was the name of that thing? I bet we might actually have all the bits we need on the. On these HID registers, even if we don't know why. Ah. Yeah, because that one's defined but not used. So. Okay, so that's the hit 10 bits. 10. Yep. And then we have C15 1 2. Which should be that one. Yep. And that gets set with bit 8, which is trap SMC. Interesting. We probably don't actually need that. But let's see. Yeah. Probably don't actually need that, because we're not going to be issuing SMCs. Yep. And then hit 9. 15 9 1. E hit 9. Yep. And then that's clearing that bit, which is bit 5. Which is in there. Yep. I think we need that. Yeah, I haven't renamed these yet. I'm still working through it. E hit. Wait, there's an E hit 0? Oh no, yeah, there's an E. Sorry, of course there's an E hit 0. And that's not used anywhere. Cool. Then it checks for 210, which is 33. And 33 is Firestorm, so we don't care about that. So I was right on the ID for Firestorm. 4678. And then it checks for 220, which is 34. Yep. Okay, so we got that right. That's funny though. Why is it sometimes checking for SE core and sometimes checking for the part number? They should be the same, right? I mean, it's like two different ways of checking for the same idea. That doesn't really make a lot of sense to me. So 220. I need some 1 2. User 15 1 2. That's that weird one, right? Yeah, you hit 20, that is correct. Why do we have this in like a whole bunch of different things anyway? And then we set bit 15, 16, and set the timer thing, right? Yeah. This is horrible. Yeah, that and then does. Oh wait, it clears. It ends and then ors with yeah. Yeah, we need a reg mask in here. No, it's the same as it's 3, but yeah, it's better to do it that way. And so in that case, we need that. Was that actually E hit 20 or hit 20? I'm kind of doubting that. It should be hit 20. Yeah, trust MC should be hit 20. Yeah. these names, but it says VLD and older, sorry, typo there. Oh, valid, maybe. That makes sense. It's the same, so mass, yep, that's good. And then, yeah, that's not used anywhere. Cool. That should be fine for the ice storm inits. And then in startup, we can do a all right. And a make file. That's fine. That's actually fine. Chickens. Alright, and then we're... what am I doing wrong here? It's not sysreg. Sysreg should be... It's sysreg. There we go. Oh, this is not... This doesn't need these things. I don't know how to write C. To be fair, the C preprocessor is terrible. Okay, and then... S3 and 0. What? Oh, am I stringifying the whole thing on that? I think I am. Yeah, I am. That's annoying. Wait, so then I can just paste it. Aha! There we go. Oh. Okay. Let's get this a shell. Yep. Ammonite storm. I think that works. And in principle, if I now do Linux without Python chickens, it should still work. And if that works, I think I'm going to call this done for the day. Not for, at least for now. Because I need to get some food. And I got some stuff to do later. Yep, looks good. By the way, how's my video? Because I have completely unrelatedly, yesterday I spent some time reverse engineering registers on my HDMI capture card. And I turned off a hideous sharpening filter that used to be there. Let me see if I can show you how it looks. Like... I need to run this on the other machine, but basically... this thing. So the colors would be different, but also like, let's see if I can show you. So it would be like this with the sharpening. And if I disable that again, hopefully it should look a lot better. But also the colors are better. I've been fixing things, so coming back here, because I had to do that on the other machine, but it's been fixed. Yeah, this thing. So Maximus64 from IRC, he's in the Asahi channels, but he was looking at this, and he's got some stuff on his GitHub to write registers on the card, but we didn't know where the different things was. So I spent some time flipping every bit in every register and trying to figure out what things are. And specifically, I found this weird black point thing feature that messed up the color gradients, and the chroma sighting was wrong, and I found some registers that could fix that. And then these standard control settings seem to look pretty decent. And but more importantly, this is not in the video processing chip; it's in the USB chip. This horrible sharpening filter. I finally found the bit to disable it, so hopefully it looks a bit better than it used to. Yeah, I actually added a little bit of sharpening in OBS, but it's a lot less extreme than the and less bad than the one in the thing. So if I think I just broke it right now. Yeah, I just broke it. Sorry. There's something wrong where if you open the OBS properties panel for the card, it dies. I have to unplug it and plug it back in, so give me a second. Hopefully this... Yes, and now everything is wrong again. This is defaults. So what you're seeing now is what it would look like without all the fixes. And if I run that script that I just made, hopefully that's a lot better. But what I was going to say is the filter that I turned on it's like this without the sharpening and without the OBS side sharpening. And this is with the OBS side sharpening. It's just a very slight sharpening to make the text easier to read because I do have it pretty small. But it's a lot less extreme than the other stuff. This is the original firmware. I haven't patched it. It's just I'm using these horrible. It already has a backdoor interface for writing memory, which is what these are using. And Maximo64 is working on that on his GitHub. It's in there. It's here. I don't know if you can see that, but this is the page. And but this is wrong. Like somehow the bit he thought was sharpening was not sharpening. And yeah, it was in a different place. But there is, it hasn't been updated yet. But there was, yeah, this page with the registers in the main chip, and the registers on the other thing where is it notes? Yeah, I think it's here. Yeah, so not here, sorry. Reg note. Yeah, so this is the old set, and I spent a bunch of time. How is this thing? I think it was in here. Yeah, so sure, record data. That's when I crashed. Yeah, so I basically flipped every bit in every register and tried to figure out what they do, and I got a bunch of interesting things. I found out there's an OSD. It's really cute. There is an actual OSD in this thing that you can just turn on and like. Hold on, let me show you. Give me a second. I'm just gonna log in from here so you can see what I'm doing. Because otherwise I'll do it on the other computer. But I'm gonna briefly. So it should be. Yeah. So if I can full screen this and show you what I'm doing. And like, for example, this stuff OSD config, right? X51, enable plane 1, and I think it needs to have yeah. Or not. Yeah. How cute is that OSD? and another funny thing is that so it defaults to uninitialized memory, so it's all garbage. But I found another register that runs a memory test. This one, 0f-bit7. And if I set that, then everything stops because the memory controller is doing a memory test. And you just get a green screen. But if I unset it, now the memory is initialized with an incrementing pattern, and so the OSD is basically showing me the char set. And then, like, if I set the start offset 57 to 0, you get all the char sets starting from you get all the char sets starting from A. And like it's a VGA attribute style thing with blinking and 16 foreground colors and 8 background colors, and one of them is transparent. And you can change the palette, and you can upload up to, how many was it? A bunch of custom characters, which are the ones at the bottom. If I increase the height, if I set 58 and 59 to 16 and 59 to 16, you will get the whole thing. And so you can see that third quarter is actually user-defined characters, and they're blinking because the high bit is set. But you can actually see the like sort of binary incrementing patterns in there because they're just incrementing memory. And then it has some cute control codes for compression, where like C1 to C8 insert spaces, so you can have one character in the character memory that doesn't actually that feels aligned to the end, or that adds a bunch of spaces, because you only have 256 characters for the whole OSD. I don't know why I reverse engineered this. It's just because it was cute. But actually, there was a very useful thing for this, which is that because the overlay was also sharpened, that was very strong evidence that the sharpening filter was not in the video processing chip. It was in the main USB camera chip. So that was what told me that I was probably looking in the wrong place, and so then I tried flipping every bit in the other chip, and hey, I found it. So yeah. Do I have references? Do you mean like documentation? No, there's nothing. This is all blind. The only thing that we had, Maximus dumped the flash, and I managed to find, and we were both looking at this. We only found each other a bit later, but I found an actual firmware update. So I had a USB trace of updating the firmware from Windows. So now we have a flash drive from Linux they can just use and don't need to use a hardware or anything. And it does have a bootloader, so I think you can't actually brick these things. I think worst case, if it doesn't start up, you could like short the flash chip while you plug it in, and it would boot from the ROM, and then you can update it. But honestly, this is on the Infinite project stack, but it's one of those where if I had time, or if someone wants to look at it, it would be really nice to have custom firmware for these things. And it's one of those things where the ROM has like functions, and then you hook them with function pointers, so you still have to use the ROM, but the firmware isn't that large, and probably it doesn't do much other than set all these things. And probably with custom firmware, we could get much better quality. There's a few things that are a bit weird here. But yeah, no. It's still pretty nice. Yeah, we got test patterns here. And yeah, the latency is okay. It's not perfect, but I don't know how I would show you that right now, actually. It's hard to do here. If I plugged another thing, yeah, no, let's not do that. It's easy to show in person. It's hard to show when I'm already using it. But yeah, I mean, yeah. And yeah, they are pretty fun. And they're cheap. It's like $30 or something like that. Okay, let me commit what I have, and not Blackbird. So, do we have any changes here? Yeah. And then we want to add this. And let me just make sure there's no garbage in here. So which ones are we not using? We're not using those. Wait, there was one more before. What wasn't? Oh, sorry. Yeah, no, actually, I forgot. I'm not done yet. There is more stuff after this in chickens.py, but it still boots without this. So these are clearly the critical fixes. But there's more. Sorry, I forgot. I need to do this one. And then we just write, yeah. I don't know if this actually, if the Apple code. Wait, 3.0, no, 3.4. And sort, yeah. MPIDR EL1. Wait, hold on. It's not 3, it's FF. It gets the whole thing. I don't know where the 3 came from here. Yeah, it's ending with FF, so this should be FF. And is that common? Probably. This checks. It's not equal 48 DC. Yeah, that's common. And then it does something else. Oh, this is just kind of overlapped for some reason. So we need to do this one. 5150, whatever that is. Yeah, those are the ones we don't need. And then C15C14 is what? Just make sure we don't lose that. Oh, sorry, not that one. The one that gets written with the core ID is this one. Oh, it is right. And C14? 641514, yeah. I wonder what that is. Wasn't in here anyway, right? Yeah. Yeah, so this we have no idea what it is. And then we have the CYC override stuff, which actually looks pretty much like something we want to do anyway. Let me do a... I suspect we want to do those psych override things. Out in common here anyway. And I guess we don't need to reboot, but we can just break and, you know, if there's no tunables, there's no tunables. So that might actually be common for all I know. That we'll figure out later if we want to move it. And then there's this CYC override stuff, which we do need. That's clearing that. So that was... one for... And we don't need these. I mean, it's the same thing anyway. And probably that needs an ISB here. It's probably a good idea. What was that thing? And then this is doing C51550. That was that one, right? Wiki docs. 351550, yeah. CFIQ mode on the IRQ mode. That is already in the... that wasn't here. Yeah, this. Yeah, so that's totally... That's just this stuff. So this isn't even M1 common. This is just at the end here. Well, we don't know this. This might be M1 common, but the rest of the stuff is definitely going in here. And we got that from here. Docs. Before you need that one, not sure yet. And then finally, what other stuff was in chickens? Oh, ACTLR. Is that in here too? That's bit 5. AFP, what's AFP? It's not even used anywhere. Where is that done anyway? That's not called from anywhere here. Mm-hmm. This is defined there, but yeah, it only sets that one bit on there. So I don't know where that came from. But that looks like a very specific thing about. Yeah, it's a line invalidated by VA to point of unification, and I'm not entirely sure what that does. I'm not sure where that came from, to be honest. It's really confusing. Like in this thing, right? DSB, but like, I'm not sure where that came from. And it's working without it. And then CYC CFG, which is and then it clears that, but honestly, that's not even right. What was that code? Hold on. Ah, yeah, this is an and. Yeah, we're there. And where is the... Hold on. Oh, okay. ACC config. And that was S3 5C15. Yeah, it touches that here. Oh, that's also when it does MPI. No, this is not PIR. That's not rated. It's checking for something, and no, is that? Ah, is it after the... Oh, this is like at the beginning of the whole thing, right? After those vectors, yeah. $5794. Hold on, let me check this. Osler, dice set, E-bar, does a bunch of stuff. APRR stuff. $1719, yeah, the KTR things here. And finally, there should be a branch. Yeah, we got here. Yeah, so set VP red, right? Yeah. Yeah, that's that thing, right? The VP retention thing. As expected. Yeah, so that's just reading the X config and does the mask. Yeah, that's that thing. Still don't know where that came from. Yeah, it's not called anywhere here. Anyway, wiki docs. It's funny how that is a command line argument. I wonder if that's a mistake and like they looked at this and it's the wrong bit. So I've got the NSID, NSID thing, and I've got bit. That's bit 11, was it? Yeah, 12, sorry. And this is bit 9, which is what? Which is nothing. I bet that's a mistake. Because the NSID is actually getting called in here. Yeah, let's do that. But actually, I wonder... What's that about anyway? Some of this isn't here. Or not. Seems to be built in. Wow, that's like not defined. Like they got rid of that definition or something. In that case, yeah, these are another HCR. Yeah. Okay. Yeah, we're not gonna do that. We'll figure that out later. It's probably somewhere else in the kernel. But what I wanted to do is that thing, just the override. The other one, this deep sleep. Ricky docs. And I think that should be all there is to it. That should be good. And we'll look at these force up, force down things later. But for now, that should be fine. Okay, what did I just break here? MSR. Sysop. These were coded. And everything in a colon. And overwrite. That. Just argue. These are parentheses there. Cool, we're getting there. And okay. This is the old source. They didn't release the M1 source, but this version of macOS supported the M1. And as I was doing this, I found out that every single chicken bit that the actual M1 binary set is in fact documented in this file. I mean, obviously what they did is they had the source with M1 support and then they removed M1 support and released it without M1 support. Or they had a fork or something. But this file did in fact have all the bits that M1 Ice Storm sets as chicken bits. And we'll see about Firestorm, but I bet it has them too. So, quote, no M1 support, unquote. All right, let's see if Linux works. As long as I didn't break anything, I'm happy. Cool. Not that one. Yeah, that. Yeah, there's CPU info. This crashes, by the way. I need to figure out what I did wrong there. But probably just missing some setting in the interrupt controller. Yeah, okay, cool. That's enough for today. I need to get some food and some other stuff done. So, yep, thank you for coming, and I'll see you later. Bye-bye. Actually, let me commit this while I do that. Actually... just rebase before exit if you're going away. So I can say that it's all committed. That's not what I want to do. That is in fact what I want to do. Hold on. Huh? And I did something weird with Git. I already had that stage, that's why. Yeah, I need to reward that, and that's a fix. Yeah, and that's fine, and the only thing we don't need is... This change should have been earlier. So I can just do this. Yeah, it was just 3. So just undo that part. And then undo it, and... And I'll just squash this into the other commit anyway, so... Guess it's just a fix to that. Okay, that makes sense. And I need to sign that off. Okay, there we go. Now it's done. That's just doing the stuff, and if I git show, this adds the chickens. That all looks reasonable. The header and that. Yep. All right. Bye-bye. Thank you.